on metal 3D printing at the Eaton Vehicle Group. With us are Georgetti and Alex from the Eaton team. I found out about their use case and their usage of metal 3D printing a few months ago, and I thought it was a pretty amazing story, which you'll now hear about. There's some great and interesting parts that folks have printed. But beyond that, these are the early days of metal 3D printing. And so seeing what's possible, we as vendors, we hypothesize what customers will do, but really it's for trailblazers and early adopters like the Eaton Vehicle Group team to really show where are the wins for this new technology and kind of guiding the path for everyone else adopting additive manufacturing. So with that, I want to introduce Georgetti and Alex from the Eaton team, and feel free along the way in the Q&A panel on your interface, feel free to ask questions. I'll be answering some of them along the way, and then all the questions that aren't answered during the webinar we'll answer towards the end. So with that, I'll hand it off to the Eaton team. Welcome, guys.
Okay. Thank you, Ilya. Thank you everybody for joining the call today. Let me go ahead, share my screen, make sure you guys can see it. Can you see okay by now?
Perfect.
Okay. So thank you again, Ilya, Nick, and all the desktop team for having us today here, Alex and I, to share our experience and how we are leveraging desktop to address our improve our operation, address our issues. So before we start, Alex and I are going to be sharing the discussion today. So Alex and I started this approach together about 3 years ago. So I'm responsible for the overall manufacturing strategy of the company and also all the Industry 4.0, and Alex leads our additive manufacturing council. He's really our additive manufacturing expert with a little bit over 10 years of experience on this field. So just before we start sharing some examples, let's just share briefly with you guys when you're gonna hear us about, say, Eaton and especially Eaton Vehicle Group, what that means. So Eaton is a big company. You can see some statistics around sales and the number of employees and what we do. But specifically to Eaton, we have essentially two main sectors, what we call industrial and electrical sector. And inside the industrial sector, we have four business, and one of those businesses is Vehicle Group, and that's the business Alex and I are part of. And inside this business, we support both automotive and truck business. Here, just a quick introduction of the two of us. As I said at the very beginning, I lead the manufacturing strategy for our group, all the Industry 4.0, and then additive manufacturing is one of the legs inside that main umbrella. And Alex, again, leads our council and leads all the additive manufacturing deployment globally. Before we start, I would like to have this slide over here, because this slide tell at least our team a lot of things. The first thing was when we start all this journey, that was all that mindset around, we're gonna there to work, we're not gonna there to work. And then one of our team members put together this phrase and say, I was afraid to fail, but now with additive, if I fail, I fail quick, I learn quick, I solve the problem quick. So this was a lot of the mindset we are changing inside our company around additive manufacturing. And together with that statement came the logo, the red one you can see on the lower right corner around, hey, keep calm, we can 3D print. So these two, the logo and the phrase, really gives you guys an idea what is the mindset, what's the journey we are going through our company. Here just to bring you a couple of guys, for you guys, a couple of a different perspective on journey, vision, the business, and how we are changing that. So our journey really started about 3 years ago when Alex and I first met, and we said, let's create a model that we can deploy additive in the same way globally. And when you say globally, we are talking about Brazil, Mexico, US, several countries in Europe, India, China, South Korea, and so forth. So really a global environment. So then Alex and I got together, we put together strategies. We put together a strategy that started with the polymer printers, and then we define one model and we spread the polymer printers to all of our sites. Our teams start learning with that. We learned that further, and then we said, okay, now it's time to go into metal printing, still for production parts and prototypes, and that's what we're going to be covering today. That gave us the new set of learning skills that our team needs, and now we are starting our journey to production parts in metal as well, but then it's a different technology than what we're going to be talking on this call. Our vision is really that all of our technical teams, when they need to address a situation in the sites, or they need to introduce a new product, that they really think about additive manufacturing as their first option when a tooling, a fixture, or quality safety device needs to be developed. And that has been a very interesting journey, a very interesting learning that is really making our teams to think differently. Is open then a lot of new design opportunities. We're going to show later on this deck an example that we're going to show what we mean by that, showing what we call an old way to do a fixture and the new way of doing a fixture, and that will become more clear for all of you. This has really allowed us to resolve things quicker and introduce products quicker. We are seeing a lot of benefits from both cost and the cost avoidance. For us, a cost out is when we already have a tooling in place, and then we are able to replace that tooling leveraging additive manufacturing. So then, in other words, we spend less than we are forecasted to spend. And cost avoidance is when we are implementing a new tooling for the first time, and then by leveraging additive, we avoid to spend more money, we spend less. You're gonna see a couple of MRO examples that is allowing us, when the machine goes down, to 3D print those parts that otherwise you're gonna need to keep on inventory or buy from external vendors. And the main one is really around the lead time. So things that we used to take 4 to 6 weeks to get a tooling from the vendors we work with, now is a matter of days to us get our toolings and our devices 3D printed. As we look for that overall strategy and everything that we spoke so far, those are the 3 pillars we're working on. So polymer, metal for tooling and prototype, and then production parts. Our focus today are going to be on this middle section. And this middle section, we have defined a studio system to be our metal printer to go on this space. You can see on the picture, by being one of the early adopters, we still use Studio One, but we are having discussions with Ilya and the team to change or to upgrade our systems now to the Studio system version 2 that's being released by Desktop as we speak. This is how our approach with Desktop Metal started. So this is one of our facilities in North Carolina. That's where we have what we call our additive manufacturing COE center for Vehicle Group. That's where you can see Alex on the picture. So that's where we learn, we develop, and not only supply this particular facility, but that's where a lot of the knowledge is developed and also shared globally with our sites. Alex, you're gonna share later on the deck as well some examples, even coming from Poland. That's considered a low-cost country, and even in a low-cost country, you're able to obtain substantial savings. Where Studio plays on all these discussions that we are having here. So for us, Studio was really a nice fit on this space. So we standardized the Studio to be our printer, and we really drive our teams daily basis to really leverage the studio as much as we can to improve our overall performance, introduce new projects, really for everything that you can thinking about. So as we continue on this deck today, and I'll turn it to Alex here in a second. Alex, we're gonna be cover first a few examples on the MRO space. Then he's gonna share some examples on fixture quality devices. And later, he's gonna share 2 or 3 interesting examples where we now combine both metal and polymer 3D printing examples working together at the same device. And this was also a big learning for us, because that's not something that a lot of companies are doing. Most companies either focus on the polymer or metal, but we were able to, in some situations, even incorporate those two together and achieve interesting results. So with that said, I'll turn to Alex, and then Alex, I'll flip the slides for you here.
All right, thank you, Georgetti. And I'm going to try to speak up. I have machines running in the background, and I'm not a loud talker, so just let me know if you can't hear me. So go to the next slide, and this is MRO and machine spare parts. And just to give you an idea real quick, maybe 30 minutes ago, I had a maintenance guy come in and pulled a bracket off of a Gleason machine. We didn't have a spare, but he had enough of one that this is for like a sensor arm, but he had enough of one to give it to me. I did a quick scan. He did a temporary, the scan took me 15 minutes. So now I'm actually creating the model so I can start a print job, which should not take, I mean, I'll have it printing before I leave today. But he's repairing that one to just get him by. So, and this is for a European machine. So, you guys probably know how difficult sometimes it can be to get a part when you need it. So that's just one example a half hour ago. This one you see right here, we did a project where we're rebuilding our furnaces. And the goal of that is, of course, to rebuild it and get it back up running as quick as possible. And when you rebuild a furnace or something, you don't really know what parts you're going to need yet. And this came up when they were doing the rebuild. And this is a guide for the chain to recirculate back around through the furnace. It's a very important part. It's a wear item. And you could probably see a little bit of the size, maybe in the lower left corner. And this is maybe 150 millimeters diameter. And this is an example of a large part that typically a large part that has cost savings because the fact that it's big and then has a lot of material taken away, leaving say a thin wall type tool or fixture or machine part. And so this one actually gave us like a 65% savings, and of course a much quicker lead time than it would have taken us to go to the OEM and order the part. Okay. During that same rebuild, we had a bracket on one of the furnace doors that they noticed had a bad crack and needed to be replaced. Again, this is another part that wasn't planned with no spare. And basically they removed the part, and I was able to do a quick 3D scan of it, and then take the scan, create the model, and then print the part, which you see in the lower middle of the part that was printed. Again, this allowed our guys to keep the path, to stay on the time and to keep the path to get this furnace rebuilt, and had a 77% cost savings versus contacting the OEM and getting these parts shipped to us. All right. So this is probably the largest. This is the largest category that you will find: the fixtures, quality devices, safety devices. And then we'll show a few examples of that. Go ahead. This is designed by our colleagues at the Chev Poland plant. And just to mention our other sites, we have a site in Chev Poland that does metal printing and polymer printing. We have a site, Valinhos, Brazil, that's a little bit newer to the metal printing and polymer printing, and doing a great job as well. We have another site in Mexico doing metal printing. All these are sites that are doing, these are manufacturing engineers and technicians creating tools, fixtures, machine parts as needed, and in combination with polymer. So what you see here was designed by our Chev Poland site, which is a Gleason rotor machine used for making the rotors for turbochargers. And we have these same machines, like a lot of companies, you have similar machines at different locations. So we have the same machines in our Georgia facility. So our engineer there needed to replace a loader mechanism. This is loads the part into the machine. So you could see in the lower right, there's like a bracket connected to the machine, and then there's like a cup that's holding the rotor. That is roughly maybe 100 in diameter, 100 millimeter diameter rotor, to give you an idea of size. So that bracket would have been a big solid chunk of metal and then connected to a cup. So the engineer there, designing for additive, designed that bracket to just, to reduce the material, put material where you need it, because it's opposite from subtractive. With additive, you're putting material where it's needed. With subtractive, you're taking material away to make it functional, but you're only taking enough away to make it to meet the functionality. This one had in Poland, had was 66% cheaper, which for Poland, that's substantial, because their cost for machining is a lot less than the U.S. Multiple times less. So that was a great job, and then we're able to deploy the similar solution at other facilities. Okay. These are robot grippers. It's an automatic, as far as your automation grippers. You either can print them solid, you can either print them in full metal, depending on the application, or you can do a hybrid approach where you have a carbon fiber filled nylon or ABS as the main body, stiff polymer, and then put the metal at the locations where you need this high wear capability. And these particular grippers grip a hardened gear. So we need the wear capabilities of the metal versus the polymer. So these little jaws here, we started in stainless, now we're in 4140. We're getting around the 50 Rockwell, which is where we need to be for our hardened parts that we're actually gripping to get this long wear characteristics. And these, because they're small, complex, you get this much bigger cost savings. And so we're seeing about 90% cheaper than our actual machine grippers. Go ahead. So this is an example, one of the first examples that I did that really shows you how you have to kind of rethink the way you do things. If you stop and think about it for a minute, your tools and your fixtures were designed for that process being machining in most cases. So in that lower left corner, that is a chuck jaw for a pneumatic chuck that's internal gripping on a gear. So that jaw started out a solid piece of metal, and they only really removed the material needed to serve the function. So it left this, big piece of metal. Now, you wouldn't take that model and say, let me just print that, because you're not going to see the full benefits of cost savings. You need it. We use tools, 3D modeling software, and there's a lot of different software out there now. But I was able to take this model, put it into our ANSYS Discovery 2020R 2.5, and give it how it's supported and give the forces that are applied to it. And then at that point, the software, literally tell it, I want to do a reduction of material by this amount. I want to keep this amount I want to achieve this goal. And I start the process, and it starts eroding away the material that's not under load or not needed to support this force. So it leaves me with this more organic shaped jaw, which is the third one to the right, which is your topology optimized jaw. This is where you need to be going when you're working with or designed for additive metal and even polymer in some cases. But you want to put metal where it's needed, and instead of taking away metal. So it's a different way to think, and it takes a little getting used to the thought process. It's not saying I could not print that jaw on the left, but it's saying I'm not going to get the full benefits of cost savings and the quicker tool to the shop floor if I don't utilize some of these newer CAD tools. So this one has 79% cost savings and much quicker to get to the shop. Okay.
Yeah, and Alex, if you'll just allow me to add a comment, we like this example internally a lot, because when we started the additive journey, we were doing a lot of on the left side, just taking something that we buy today or we designed the old way and just printed it, and we start realizing some benefits. But then, as Alex was describing, really learning the technology, learning all the features that we have on the software that allow us now to do designs like you see on the right picture, and try and experiment that. That's when allowed us really to start boosting savings as we are not being able to do before. And this design was the one that helped us to motivate the team in Poland to do the other design that you guys saw, really not only looking on the portion that was holding the piece, the piece being manufactured, but also on the tooling that's connecting that piece to the machine bed, and really doing that design instead of being a complete piece, being more a surface with a lot of different structures in the middle, allowing also for weight reduction. And this is the example we tell our teams internally around. A couple of years ago, you'd design something thinking about, okay, I'll start from a block, I'll start from a bar, and then I'll do a lot of machining and looking if I could do the machines to get to the design. And now it's completely the opposite. So we are coaching our teams to say, just add metal or just add material, whatever we need to add material. So I'm just reinforcing these points because we like this example a lot internally as a completely mindset change inside our organization. Alex?
Okay. So this is an example of assembly tool. This is a bearing press tool, and what the purpose or the function of this tool is to press bearing races in. Before, they would have actually changed out a larger piece of tooling here, and the engineer came up with a solution to make like a drop-in tool that actually is thin and kind of insets into the current tooling to do a quicker changeover. And actually, being this is thin, I was a little worried about the application as far as would it survive, and it actually survived well. And that's one thing too that you don't really think about, but printing thin is sometimes easier than machining thin. So you can start by printing a thin wall and then do a finish pass over it instead of hogging away the material. That can actually benefit you. And we've done both polymer and metal, several thin parts that would be difficult to machine. So this one actually has an 86% cost savings versus machining, and you could see you would have had to take a lot of material out and get to a thin wall part. Okay. So with metal additive and with polymer, but specifically metal, you really have some big advantages in design when you have applications that have flow. So now you can have all these curved geometries, complex geometries inside the part that you could never really have before. And this is an example of that, where we're actually designing fast fill, oil fill nozzles that we would not have been able to do before. That because of the geometry that's internal inside this nozzle, we're able to fill our final product, or at our test stands, fill the oil much quicker than we would have been able to with conventional machines or supplied nozzles. And that's 94% cheaper, and that's because of we had it quoted, but a lot of that's all the internal geometry that this technology allows you to produce. Okay. So, going from metal, where you really see a lot of gains is where you combine both polymer and metal from a manufacturing engineering standpoint to solve problems in the shop. And these are some examples of the hybrid approach. Go ahead. So in our Gear Lab, we have like a collet that they use to attach shafts together, and it was a polymer type collet before that was breaking from fatigue over a period of time, but they connect these two shafts together, and then they're able to do a gear check using the equipment in the lab. And this is a high frequency check it's a production inspection that they do. And we were able to rethink this collet. We wanted it to be metal, but we didn't want metal to metal contact on the final component. So we printed a metal collet, if you want to call it, and then we printed a TPU, elastic thermoplastic TPU, which is super durable, and we use that in combination with the metal. So now we have this elastic material that's contacting the part and not scratching our part. So this is a good example of both 3D printed polymer TPU and metal. This one has roughly about 84% savings. Okay. So another example is a lotto device, lockout tagout, and we have these in all combinations, shapes, and sizes. So this is one that I think that's really good because it's a polymer arm in the black color that you see, and it has a 3D printed metal like a latch that actually connects in the bus box. So what the maintenance technician would do is he attaches it. This device is permanently attached to an extension pole, and instead of going and getting a lift, the maintenance guy just gets the pole with this device attached to it, he reaches up and to where the lever is, turns off the power, and engages using a cable where he's on at the shop floor level. He has a cable, and he actuates the cable, which engages the lever, the metal 3D printed lever, into the lockout part of the bus box. But he's doing all this from the shop floor level. So now he really didn't have to he doesn't have to get a lift. He doesn't have to use a harness. It's much safer for him, it's quicker for all the people around. And we use metal printing as part of that solution. And this solution, if we were to go out and try to have it manufactured, would be substantially more. We're getting about 94% savings in these devices versus machining. And we have several different types of bus box, so we have different ones that we use. And this is a good example of a safety device. Okay.
Okay. With that said, Ilya, we are back to you to help us on any questions or comments from the audience.
All right, fantastic. Tons of questions. I'm going to try to keep up. So, generally speaking, what testing do you perform on parts, either in process or on the finished parts? Do you do any unique testing that wouldn't apply to other manufacturing methods?
I'll start, and Alex, feel free to add. What we did is, of course, we did not jump to all these examples, or let's say more complex examples that we are sharing today from day 0 to day 1. As you are learning this metal, Alex and I, we set up 3 different groups of parts. So as more as we learn and print one piece, put in the machine, and see how that runs, and measure hardness, those type of things, we start building our confidence around that, and then it started evolving to more complex toolings until we get to the point that we are now today, where we can have important press forces, or we can have significant spindle rotations to that point. But it's essentially trials, experiments, and measuring the hardness of those devices as we sinter them, and sometimes even do additional heat treatment process. And when we get to a situation that's something that's not that we have designed anything similar, we usually do one, and then we try that together with the production team before really releasing to full production, a more kind of contained environment.
Thank you. Next question, how many cycles or usage hours do the printed loading arms last, and how does it compare to the OEM parts? And I guess let's expand that in general. What have you seen with the lifetime of the printed components versus their alternatives, whether machined or cast?
I'd say that there were just a few examples that we did that we end up having a lower life. The vast majority of the things we did so far, they had at least the same life as the components we used to buy from external vendors. I would say, Alex, if you agree, I don't know if you agree, but I would say probably what 90% of everything we did at least the same or better.
Agreed. Yeah.
Terrific. All right. Oh, this is an interesting one that I've seen once before. Are there any IP concerns with the part where you scan and copy from the original? I suppose in the case, sometimes the design is you're replacing a component from another vendor. So you're, scanning it and then printing it. Are there any IP concerns you have there?
Yeah, so there are two aspects for that. So a lot of the tooling that you see here, a lot of that tooling we developed internally, and we gave the drawings to our vendors to produce. So those, in the end of the day, are ours. And the ones we shared here, they are really old equipments that we really did not have a drawing, and some of those were even vendors that are not even anymore on the market. And when we scan it, it's not only scanning and print it straight away, but it's scanning and work on the design to do even in a different way. So from our perspective, we are not going against any of the IP topics.
Terrific, thank you. Related question, what's the typical scan accuracy and then printing, and really, let's say printing and sintering tolerances for key features like, inside diameters of bores or hole-to-hole location, thicknesses, etc.?
The scan actually is going to be dependent on your scanner. What we decided to do, I've used some light scanners in the past, and they were time consuming. We decided to go with a solution that we could get from part to scanned STL in 15 minutes, 10 minutes. And we're within, the accuracy is less than 30 micron. So we're using the Creaform HandyScan Black handheld metrology scanners. They're not a cheap solution, but in comparison, we compared quite a few. Engineers don't have a lot of time to sit in front of the scanner all day. You have a machine down, you want to get just, like happened today, I don't want to hold this part long. I want to get a measured scanned part into an STL format as quick as possible. And I was able to do that in less than 15 minutes. So I used the Creaform HandyScan Black. What was the other part of that question about the
tolerances?
So your internals typically are smaller and your externals are larger by the shrink, after shrinkage, that you're after sintering. And we're typically, depending on the part size, we're typically within the 0.2 millimeter diameter on the internals. Externals in say the 50 millimeter diameter, we're in that same ballpark. That might be different than what's publicized, larger, but at the same time, if you're going to make multiples too, you can take that part and you can measure it after sintering, make adjustments. That repeatability, part-to-part repeatability, is less than that. You can always, do a one part through, make an adjustment. If it's a critical dimension that you need, say if it's a mating surface or it contacts, it's the part of the fixture, something that contacts the part for machining, you would do a post machine on the mating surface and the contact surface. Those two places would get like a post machine. So we'd leave a little bit of material to do a clean, a finish pad.
Got it. Thank you. Next question is, how big is the Eaton Additive Manufacturing Group, kind of both the core team and on-site practitioners? And then the other piece of it is, how big is the group of engineers, colleagues that you serve across the four sites?
Okay, so to address the first question, when we say that the number of additive manufacturing colleagues that we have, the same group that is supporting polymer also supports the metal printing. So from a polymer perspective, we have about 22 printers spread globally, and for this metal around 4. So regarding people, we have Alex as our council lead. Everything that we do through a global council. So Alex leads that council, and then he has one representation from each one of the regions. So this is what we call a core team. And this core team is going to be probably 6 to 7 people. And these are the guys that help us to then spread the knowledge and spread the best practices among sites that are located globally. Every site we can say we have about 2 to 3 people in average that are capable of doing 3D printing. Some of sites more, some sites less. So putting all together, we probably have around 60 to 70 people that can do a 3D printing today, but they are not dedicated to additive manufacturing. This is just another task, part of their daily activities.
Got it. What software do you use for topology optimization? Let's say in particular, let's say you were removing material from the jaws.
So we use, well, we have a Center of Excellence for Additive, and in that group is, you know, some software, IT software specialists, and they've used them all so far, and they test them all. But the ones that we've come to right now that we utilize the most, we utilize the ANSYS Discovery, ANSYS Discovery Bundle. That's 2020 R 2.5 is like a big change to the versions, and that allows us to actually do live FEA, make changes, and then once we get it to where I want it in the software, then I'll start the topology optimization module that will then start removing the material away from my design and leave me with the part that meets my criteria, but's been optimized for additive metal. The other one, I guess, that we're also starting to venture into is Creo 7. Those two are probably additive software, the two that we're focusing on the most, that have some pretty sophisticated topology optimization modules.
Thank you. Do the cost numbers that you shared include amortized cost of the 3D printing system, or is it just material, consumables, labor, electricity?
No, that includes everything, and that was also a big learning for us, because we have those printers on manufacturing locations that we have worldwide. And initially, when we were looking for the cost, we learned that we were overcosting 3D printing just by leveraging overhead rates from those plants. So what we did is learning from Desktop all the parameters around the fluids for the debinder, the amount of gases that we use when we are running the furnace, and getting the material cost from the software itself. What we did was to get together with our financial team, and then going through each one of the different account streams inside the overhead, looking one by one and seeing, for this particular area of my plant, how much you really am leveraging the overall support cost of the plant in a way to really come up with a true 3D printing cost. But that cost model has all the labor, all the overhead, material, consumables, and also the depreciation for the equipment.
Thank you. Next question. Do you have any strategic plans for the aerospace and aeronautics sectors? On the one hand, there's some big technological and potentially cost opportunities with additive manufacturing. On the other hand, there's increased possibility of risk.
Yeah, so internally, as we are sharing the very beginning under the industrial sector. So Alex and I, we are vehicle group, but similar to the two of us, there is a similar group working specifically on the aerospace. Their focus so far has been more on production parts, and our has been more on an internal device. But we change our learnings and our experience. So now they are moving more towards the internal devices as well, and we are moving more towards the production parts. But on aerospace, what happened is they have additional standard safety protocols they need to follow, and there is a much higher intensive work that's done with the major air flight companies regarding validation.
Got it. All right. Prior to acquiring this 3D metal printing technology, or even being aware of it, what was the single most compelling reason or pain that you guys were experiencing that made Eaton and your team move in the direction of metal additive?
Yeah, so when we really embraced the Industry 4.0 transformation or revolution, as everybody's calling, we started to say, this is a broader term, but looking on our strategic advantages, looking on the issues we have internally, we defined what would be the focus we were going to be putting around that, and that's when additive became one of the 10 elements that we decided to focus. And then specifically to additive, that's when we said, okay, let's start small, learn, and then we evolve. So that's why we start with polymer, because the cost of the equipment is lower and it would be a easier learning process. But then as we are learning and advancing, we quickly realized that the polymer would not address the majority of the toolings that we use. And that's when metal printing came into the table. And then that's when we start the discussions with Desktop and other companies, but we selected Desktop as our printer on this space. And now we are doing the similar thing. So now with all the learning that we got on the metal printing, doing internal device, now we are taking all that learning and now moving towards production parts as well. But then it's a different technology that we have selected because of the demand, because of the mix, because of the automotive environment as we go through real production parts.
Thank you. Next question. There are, and this is not a plant by us, there are many companies that provide 3D metal printing solutions. Why do you choose Desktop Metal instead of other companies?
That goes back to the previous question. So additive is a strategic piece for us to improve our operational performance, and that is a strategic mindset change around really doing things completely different than we used to do. So that became a straight decision for us to invest instead of just buying from vendors on that space.
Thank you. What metals have you printed on the studio system? What alloys? Is it most 17.4 pH stainless steel?
Yeah, 17.4 is what we started with because it has about a 27 to 30 Rockwell hardness, and so we started with that. And you don't have to post heat treat that one. That's coming out of sintering. It's a very good material to work with, and after that we've moved into 4140. So we're doing a lot of 4140 and doing our kind of sintering. Doing, if we need to do any post machine on any surface, we'd do that after sintering, and then do our final heat treat, which puts us in the we'll say close to 50 Rockwell.
So that's
hardness.
That's the big reason to use 4140s for the
yeah, because we have hardened parts that we're clamping, and so do probably some of the other people. So you don't want to use something soft. You can. Some situations you want to, but you're going to be a high frequency of changing out wear components. So in a lot of situations, we'll want to put as hard a tools as we can in that application, so we don't have to change it as much.
I'm guessing this might be from one of your colleagues. Are we using any printers at the Kearney facility? That's a very old site that could probably use the flexibility of the printers. You guys know what?
Yeah, I can take that one. So Kearney does have a printer, but it's not metal, it's polymer. And even on the polymer space, we defined the two printers that we standardize. One for sites where we have a higher mix and lower quantity of devices that we need, and a different printer for sites like Kearney where we have a lower amount of tooling, but we consume a higher amount of those devices just because on that site we produce millions of pieces. But Kearney has not gone yet through a metal printing, although Alex is now working with all the sites in each one of the regions.
These are Kearney right here, ready to ship.
Okay, good, because we as we have one printer in each one of the regions, he's work with the sites in that region, although the printer is not on that particular site, but to those sites also leverage the metal printing that's inside that particular region.
Fantastic. Thank you.
I don't know if you want me to do this real quick, but this is one of the parts that I just pulled out of the printer. This is on the large side, but this is a cup. So this has the raft art still intact. So this is just straight off the printer, and you can see kind of what you get. No post work, and this is on the larger side of what the I would say what we typically print, but is doable. And so kind of wanted to show you that. Yes.
Nice.
Check it out.
Don't drop that. That's like the hardness of a crayon, right?
Yeah.
All right. Let's see. Next question. How reliable is the printing process for new parts? Maybe let's expand the question to printing and sintering. How reliable is that process? Approximate percentage. For example, you receive a new design, go to print it. How confident are you that it'll print successfully?
So it comes with time, and it's this has a learning curve over, say, if any of you guys have Stratasys machines, you pretty much drop your part in there, hit print. This takes more thought process, and the thought process is, yeah, you can print just about anything in the printer. So you change your thought process as how's it going to center. And so you present your part in a method using the Fabricate software that you're going to have a successful center. And so I guess, if we have a crash, so typically my first thing would be to go to the customer support and share my printer profile, my print file. And in the software, you click a button, it goes directly to them. I send them an email with the picture, and then in many cases, they'll reply, just in all cases, they reply back the same day. But even in some cases, if it might be a difficult part, they'll actually go and try something and print in-house, and then send us the solution that'll make it work. So there's also a learning curve. If you have a failed part, I really recommend pushing through and figure out why that happened. And so you start building that knowledge base of engineers, knowledge base of how the process works and how to process your parts to be the most successful.
Great. There's a kind of a two-part question here. I think I can answer part of it and then turn it over to you guys. Regarding the different technologies that Desktop Metal offers in terms of sintering, when sintering parts with overhang, there's a risk of sagging. The studio system will print support material, but if I understand correctly, the shop system is able to print without support material. How does this influence the risk of overhang sagging during sintering? So you can print parts that are self-supporting. There's some strategies on how to handle overhangs. Both systems are able to print with supports. So the answer, do you need supports or not? There's a number of options available in the software. And one additional one in the shop system is that there is live sinter software that allows you to simulate how much things will distort during the sintering process and allows you to pre-distort the printed part by that amount to kind of offset however much it might sag. But that's little on the shop system and in theory. Let's see what the Eaton team can tell us about in practical terms on overhangs.
Yeah, so this is what we call our group 3 or high risk safety type of devices, and we have not done a lot of work on that space yet. We have a good learning, but we are still in learning mode, and we have decided not to go down that path yet for safety reasons. So we'll not be able to comment a lot on this particular type of tooling today.
But as far as printing, unsupported, we typically do most of our holes with no supports, as far as if they're printed up in the Z. And I think it's, if I want to say 10, 15 millimeters or 10 to 15 millimeters bridging. And some of you guys may know about that, what bridging is. Depending on it, a lot of it depends on the weight that's above that object. So if you have a lot of weight above that object, it could collapse. So we utilize the I guess you could say the DFAM guide in some of the situations for recommended printing settings.
Yep. So some holes work just fine, 10 to 15 millimeters. You can also do teardrop shape that are kind of
use that as well.
Perfect. All right. Next question. What is Eaton's measure of success for additive manufacturing? How do you guys think about that? And you must have exceeded that in a sense, exceeded some threshold in order to roll out now to 4 sites this metal printing system.
Yeah, so that let me take that one. That has two angles. One angle from the financial perspective, and then I can tell you everything that we do on Industry 4.0 needs to be less than 2 years payback. We don't do anything on that space that will take us more than two years, unless it's the very first time we are learning that technology. So essentially, you buy that to learn because you have a business issue that you are trying to address, but it's the first one you need to learn. But in general, we don't do anything that's more than 2 years. So that one part of the answer. But the second one is really around how our teams are really leveraging that technology, and that's where we measure that from both a lagging perspective and a leading perspective. The lagging perspective is the cost out and cost avoidance that I referred in the very beginning of this section. The leading perspective, we look on that from 2 angles. One is on the printer utilization. We don't necessarily count the number of parts, but we look how much of the available time the printer has and how much of that we are really leveraging. So that's one of the lead indicators. And the other one is the number of projects that we are doing divided by the number of users, because one thing we don't want is just to keep printing the same stuff over and over. We want to increase more and more the number of different things we can print, and that's why we track the utilization, but you also track the number of new devices we are adding to our portfolio for each one of the users we have trained in our sites.
Terrific, thank you. Looks like this is one of the last questions, and if folks have any more they want to sneak in before the end, type them right now. What sort of post-processing have you done? It sounds like you've done some machining for critical dimensions or tapping or chasing threads. You mentioned heat treatment, media blasting, anything else?
Media blasting. Typically, after debond, I'll do some cleanup if I have, say, a seam area or something where the print layers may come together. But in most cases, I do a media blast. And if I have a printed thread, I'll chase it with a tap. And if there is a critical dimension, small tolerance, then we'll do a post machine prior to a heat treat.
Terrific. All right. Well, thank you, Alex, Georgetti, very much. I want to thank all of the attendees for sticking with us for the last hour. And I learned a ton. Hope you did too. This is really, really inspiring to see what people do with rolling out this new technology across their organizations. So really appreciate everyone's time. And we'll be sharing this recording in the coming days or weeks. So with that, thank you all and have an awesome day.
Thank you, everybody.
Okay, thank you.